Hi guys, welcome to R2E, and this is me Ramanoj Raman, and this is a problem from Herbert Goldstein. So this is actually a derivation from chapter 2 of Herbert Goldstein on classical mechanics. So let's see what this problem says. So I mean it's an instruction which says me to complete a solution of Brachistochrone problem that was given in section 2.2 and show that desired curve is a cycloid, the cusp at the initial point at which the particle is released, and show that if the particle is projected with the initial kinetic energy of half mv naught square, the Brachistochrone will be still a cycloid passing through 2 points with the cusp of height z above the initial point given by v naught square equal to 2gz. So this problem, let's try to first solve the Brachistochrone problem. And for those who don't know what is Brachistochrone problem, yeah, the problem is very simple. So let's say you have this horizontal line and you have a vertical line, right? So what I'm doing is, what I'm trying to say is uh, that you have a particle somewhere here. Now it's getting released. So I need to find a path between, I need to find a path between 2 points, let's say 1 and 2, such that, let's say on this path, my time is minimum, my t is minimum, right? So how to find that? So t12 is actually an integral from 1 to 2, that is ds upon v, right? So what is my ds? So ds is a small length element that is given as dy squared plus dx squared. So that can be further written as 1 plus y dot squared dx. Now if I put it here, so that goes as t1 to 2 integral from 1 to 2 root of 1 plus y dot squared on v times dx. Now till here, so everything is fine, but you should realize that since the ball is or the object is falling under the influence of gravity, and initially it has zero kinetic energy, but as it's falling and it will reach some point, so there it will have some kinetic energy depending on the height it has fallen down. So if this is my x-axis and if this is my y-axis, it denotes how much the height it has fallen. So by law of conservation of energy, so by conservation of energy, sorry, by conservation of energy, I have 1 by 2 mv squared equals to mgy. So m and m cancels. So that leaves me with v equals to root of 2gy. So when this integral just turns to t12 equals to integral 1 from 2 root of 1 plus y dot square divided by root of 2gy times dx. Now this function, okay, now this function out here is actually my let's say this function is my f, and my f is dependent on y and y dot. There's no x dependent here. So now by using the principles of calculus of variation, I will use Euler-Lagrange equation. Euler-Lagrange equation, and that is given as the fundamental form that we know is of something like that, right? Del f upon del y dot equals to 0. But the equation that I will use is of this form: del f upon del x minus of d upon dx f minus of y dot del f upon del y dot, where y dot denotes the derivative with respect to x. Huh. And this might look a little different because normally in physics we tend to show time derivatives as dots and x derivatives are dash, but here I'm using it. I'm changing the convention. So yeah, so I will use this equation. So this is just nothing but just an alternate form of Euler-Lagrange equation. So here, as you can see, my function is just a function of f and y dot. So dx will be 0. So I'll use a different pen. So my Euler-Lagrange equation would be something like now. Okay, I'll not write this part. So yeah, so this part df upon dx will be 0. So that will just bring me f minus of y dot del f upon del y dot equals to some constant c, some constant a rather. I'll use a because a lot of constants will be, I mean, two constants will be involved, and a and b seems to be my natural choice. I feel a little easy with a and b. All right, so now I have to just evaluate this one derivative. Now it is better, this choice is better given that my function is just a function of y and y dot, not the function of x, in the sense that that I don't have to take one more derivative. I mean, here if you can see, only one derivative appears with respect to y dot, and here two derivatives appears. So I mean, it's beneficial for me in that sense. And if you look at this carefully, this thing right out here looks pretty much like the Hamiltonian kind of thing, if you remember it clearly. So this thing right out here is is if you look at in terms of Lagrangian. So this the form of the function right out here is actually like the form of the Hamiltonian, because in Hamiltonian also you define it like something like if I'm not wrong, PQ dot minus of Lagrangian. Yes, so that's the form, PQ dot minus of Lagrangian, or Lagrangian minus of PQ dot. There's just a difference of negative sign. So yeah, so this looks like clearly the form of the Hamiltonian. Anyways, so now we have to solve this one further. So let's get on the job. So I have to compute this thing first, del f upon del y dot. Now that will be del f upon del y dot, that will go as root of 1 plus y dot squared divided by root of 2gy. That is, that will go as root of 2gy 1 by 2, that is again 1 plus y dot squared 2y dot, and this is it. So now that goes as y dot divided by root of 2gy 1 plus y dot squared. All right, that's good enough now. So let's put this here. So my function already was, the function was, what was my function? Yes, that was 1 plus y dot square divided by root of 2gy minus of y dot squared divided by root of 2gy root of 1 plus y dot squared equals to a. All right, so I'll multiply here both by 1 plus root y dot squared. That will become 1 plus y dot squared divided by root of 2gy times 1 plus y dot squared minus of y dot squared divided by root of 2gy divided by root of 1 plus y dot squared equals to some constant a. Okay, y dot. So now that I take the LCM, so this will become, okay, bigger root 2gy 1 plus y dot squared, and that just becomes 1, and here it becomes a. Now I square the both sides and take the inverse, so it becomes 2gy 1 plus y dot squared, and whatever that becomes of the constant, I just write it as b. Okay, so now let's get to the next stage. Okay, yeah, so that is will become 2gy plus 2gy y dot squared equals to b. So this implies that will be now 2gy y dot squared equals to b minus of 2gy, and y dot, I mean, I could have done it here in a different way also. Why I didn't do that, I don't know. I could have just taken, all right, anyways, fine. 1 minus of b minus of 1, no, not that way, b minus of 2gy divided by 2gy. Now I will take 2gy common, so my differential equation will just becomes y dot squared equals to some c minus of y divided by y, and now it just becomes y dot equals to root of c minus of y upon root of y, and this implies that dy upon dx equals to root of c minus of y upon root of y. This implies that root of y dy divided by c minus of y, and that is equal to dx. All right, great. So, okay. So I have the equation, differential equation, dx equals to root of y dy divided by root of c minus of y. Now I need to integrate both sides. So by integrating both sides, by integrating both sides, you can do it as an exercise actually. C minus of y. Anyways. So I'll do an indefinite integral right out here. Uh, Nothing special of y from between what 2 points I'm integrating. I'm just integrating it right now. Anyways, yeah. All right. So let's start off with integration. So how the integration will go? The first step will be put root y equals to u. So that makes du. Okay, that makes 1 by 2 root y dy equals to du. And so this implies that dy equals to 2u du. Okay, and y will just simply be u squared. So let's just put all this in here. So x becomes integral u squared du 2 divided by root of c minus of u squared. All right, done. Now again, I will put another replacement. So I'll put u as root c. Anything you want to put. Uh, what would be better choice? Let's put u equals to cos some v. All right. So du will be minus of root c, okay, sine v. Okay, let's see how this choice works. It is integral to outside 2 u squared is c cos squared v. Du is oh, oh, okay. Anyways, we'll do it. We'll do it. Okay. Took an extra c2 here. So that will be only c minus of root c sine v dv. Exactly. Huh. And there is dv. Yes, so that becomes, down here it becomes root of c minus of c cos squared v. Yes, so it becomes 2 minus of root c cos squared v sine v dv, and that becomes root of c sine v. So sine v and sine v cancels. These two again cancels. And I'm left with this thing. Uh, Minus of 2. Now I'm actually doubting my choice of taking it as a cos. But anyways, now it works. Who cares? Anyways, it's working. It's going on. So c cos squared v dv. So let's solve this one again. So we have cos 2v equal to sine squared v minus, sorry, it is cos squared v minus of sine squared v. And then I will write sine as 1 minus cos squared. So that becomes 2 cos squared v minus of 1. And cos squared v will just become cos 2v plus 1 by 2. Yeah, so I'll have to put this choice here. So my x becomes minus of 2 integral. See, I can take it outside, and that is cos 2v by 2 plus 1 by 2 dv. All right, now that is x equals to minus of 2c. Okay, let's just take this integral inside. So that becomes minus of c integral cos 2v dv plus integral dv. Ah, that's fine now. Minus of c. Now this integral becomes integral of cos 2v 2 dv upon 2 plus v plus some constant d. D is not a nice constant actually. I'll put some e. Okay, so this is it. So sine's derivative is cos. So cos integral is sine. So here it will get sine. So it will be sine 2v by 2 plus v plus e. That's a good choice. So now it becomes minus of c sine 2v upon 2 plus uh, minus of cv plus f. So my x goes as minus of c sine upon 2, and that is twice. Now let's substitute the things back. So my v was, so my v is actually, from here my v becomes u upon root c cos inverse equals to v. Yes. Okay, so 2 cos inverse of, okay, so this is quite big one, cos inverse of u upon root c, great, plus what is v now? I hope I haven't made a mistake right out here, na? Yeah, I think so. I haven't made a mistake. Yes, I haven't made a mistake. Most probably. If it's going still fine, I hope. Tell me in the comment section, please, if I made a mistake somewhere. Uh, yes. And what happens right now? So minus of CV plus F. So here it goes, na? Uh, so there is a negative. There is also a negative sign here. Okay, there is a negative sign here. There is a negative sign C, and V goes as cos inverse of U upon root C plus F. C sine by 2 cos inverse of U upon root C minus of C. Oh, now okay. Sorry, I can't. I don't want to waste a step. So now I will replace U with what? Where it is? So now I will replace U with the root Y. Is root Y. So that becomes minus of C sine by 2 2 cos inverse of root Y by C. Okay, minus of C cos inverse of root of Y upon root of C plus F. So this is the solution to Brachistochrone problem, which is not yet complete. The problem given in the exercise is not yet complete. I have done one part of it, and I have to show that this is a cycloid. Now I have to show this is a cycloid. How will I show that? How am I planning to show that? Well, one way could be I will just plot it. So one way it could be I will just plot it. So let's try to plot this in Python. Okay, so what I just did till now is that uh, solved a problem. I got an analytical solution. So in this part of the problem, I had to show that it is a cycloid. So I'm not planning to do it mathematically. I'm like showing it analytical. But we'll try to plot it and we'll try to see that if it's really a cycloid or not. If we have done something wrong somewhere, and if it's wrong, then definitely this video will not be uploaded in any time. Like I'll make a different video and then I'll upload that. But I really hope I get to upload this video only because I don't want to make a new video. It takes time takes time. Anyways, let's try to show that it is really a cycloid. So first what I'll do is I'll try to see where I am. Okay, so I'll go to somewhere personal. Okay, so I think this folder will be nice. Yes, so I'll move to simulations. Okay, so here I'll try to make a Python file. So what will I name it? Brach.py. And now I will open it using nvim. Okay, so one more thing that I want to before. Okay, great. It's done. So what I need to start off with, first of all, I'll import some libraries. Import numpy. Oh, pi is np. Import matplotlib dot pyplot as pld. All right. Two things I've imported. So let's just do one thing. Let's make a list. So y equals to, okay, just happening. Okay, y equals to p dot a range from 0 to, okay, from where the y will start. So it's falling from upside down now. Just a second. P dot a range, and I'll want it from 0 to 10. Okay, how many points? Or I forgot actually the documentation. How what I used to use. So I'll just let me use in space. Between 0 and 10, I want some around 500 points. 500 points. I really don't know what kind of errors it's showing. But anyways, whatever. Because this is my y. And how my expression as x goes as x equals to. So for now, I'm just putting some values for the constants. I'm putting c to be 1 and f to be 0. So let's do it that way. We dot sine. Okay, so that will go as 0.5 multiplied by np dot sine, and that is 2 times np dot r cos of np dot squared of y divide. Okay, this is great. So that is my first argument, and the other one is minus of uh, np dot r cos. I hope this really exists. P dot squared, that is again y. So this is it. This is my y, this is my x, and next is plt dot plot uh, y comma x, plt dot show escape. Now I will love Python. Okay, this thing then. So it has shown something, and it seems pretty accurate in the sense that this is going on and on and on, and it's taking a cusp like that. Probably there is a issue with my some constants, but definitely it's taking the values as I wanted, and there's some error that it has shown that. Oh, so definitely there are some points where there are some errors, which is totally fine. Let me see it completely, which is totally fine. Like there might be some points where we lack continuity. So let's try to see it for a bigger range. But it indeed looks like a cycloid. I mean, half of the cycloid if you really see it. So let me close this first. Let me again try to do this. So let me increase the range. Um, some, let's say 50. That will work pretty nice, I hope. Escape. And okay, so there is definitely some issue with this. That it's showing up to this only, not the part afterwards, but definitely in this part, it's clearly it clearly looks like a cycloid. Okay, so with this, I am done with with these parts of solution. So what I did was I actually showed that it is the desired curve that I was looking for is actually it indeed look like a cycloid. Now in the next part, now let's try to, in the next video, I'll try to solve the second part, or in the same video. I don't know yet, but we'll see. So I'll try to show that if the particle is projected with this velocity, then it is again a cycloid, and it passes through this point and something like that, whatever it wants to say. Anyways, so thank you for watching my video. See you later.